Okay, let's dive into this. Welcome to our Grade 8 Physical Science Explainer on the fundamental building blocks of matter, atomic structure, isotopes, and ions. Today, we're taking a seriously fascinating journey into the microscopic domain. We're going to uncover how tiny, invisible particles define, well, literally every single piece of matter in the universe.
Here's our roadmap for today. First up, the subatomic particles. Second, identifying the atom. 3, isotopes and average mass. 4, understanding ions. And finally, a recap and transfer challenge.
Let's jump right into Section 1, the subatomic particles. We're going inside the atom.
So to really grasp the atom, you've got to understand the sheer immense scale of empty space inside of it. Modern atomic theory reveals that an atom contains an incredibly tiny nucleus surrounded by a massive volume of space. How small are we talking? Well, the diameter of the nucleus is about 100,000 times smaller than the atom itself. To put that completely wild scale into perspective, if the nucleus were the size of a single blueberry sitting right on the 50-yard line, the atom would be the size of the entire football stadium.
Inside that stadium, and specifically packed into that little blueberry, we find our subatomic particles. Let's define our 3 core pieces. First up, the proton, which carries a positive charge. Second, the neutron, which is uncharged, totally neutral. Both of these are packed tightly right into that tiny central nucleus. And finally, we've got the electron, which carries a negative charge and just zooms around, occupying that massive volume of empty space surrounding the nucleus.
Now, what's really interesting here is the distribution of mass. Protons and neutrons, they make up practically all of the atom's mass. They each weigh about 1 atomic mass unit, or AMU. But the electrons zooming around the outside, man, they are incredibly light. I mean, it would take about 1,800 electrons just to equal the mass of a single proton. So almost all the mass is right there in the tiny nucleus, while almost all the volume is just that empty electron space.
Moving on to Section 2, identifying the atom. We're looking at atomic and mass numbers.
Okay, so this brings us to 2 absolutely fundamental definitions, the atomic number and the mass number. The atomic number is simply the number of protons in the nucleus, and this is the defining trait of an element. If an atom has 6 protons, it is carbon, period. Regardless of the neutrons or electrons, 6 protons means it's carbon. The mass number, on the other hand, is the total sum of those heavy particles we just talked about, the protons plus the neutrons.
Let's pause and actually put this to the test. If we know the mass number is just protons plus neutrons, let's apply it. Say an ion of platinum has a mass number of 195 and contains 78 protons. How many neutrons are in there? Take a quick second and do the math.
All right, if you calculated 117 neutrons, you are absolutely right. The immediate reasoning here is just simple subtraction. Since the mass number is the total sum of protons and neutrons, which is 195, and the atomic number gives us the exact number of protons, which is 78, we just take 195 minus 78. That leaves us with exactly 117 neutrons. Pretty straightforward, right? All right, Section 3, isotopes and average mass. Let's see what happens when we start varying the neutrons. So when you actually change the number of neutrons in an atom, you create what's called an isotope. We define an isotope as an atom that has the exact same number of protons, so it's still the exact same element, but a completely different number of neutrons. And because of that, it has a different mass number. Now, we obviously need a way to clearly communicate which specific isotope we're talking about, right? Here's how we model isotope notation. Step 1, write out the usual chemical symbol. Let's use Mg for magnesium. Step 2, write the mass number as a little superscript right to the left of the symbol. In this case, 24. We read this out loud as magnesium 24. Every single magnesium atom anywhere has 12 protons, but the specific magnesium 24 isotope has 12 neutrons, giving us that overall mass number of 24. And this brilliantly illustrates a crucial distinction you're going to see a lot in chemistry. The mass number is a whole number. It's the exact literal count of protons and neutrons for one single specific atom. But when you look at a periodic table, you'll see the average atomic mass, which is usually a decimal. That decimal is actually calculated from a weighted average of all the naturally occurring isotopes of that element out in the real world. Let's look at boron for a second to see exactly how that works in practice. Scientists use this incredible tool called a mass spectrometer to find these exact abundances.
In nature, about 19.9% of boron atoms are boron-10, and the remaining 80.1% are boron-11. When we mathematically weight those masses by their percentage, we calculate boron's average atomic mass to be 10.81 AMU. But here's the wild part. There is no single boron atom out there that weighs exactly 10.81 AMU. They weigh either 10 or 11. The 10.81 is literally just the natural average.
Okay, Section 4, Understanding Ions. Let's talk about gaining and losing electrons. Usually, atoms are completely electrically neutral because their positive protons and negative electrons perfectly balance each other out. But when an atom gains or loses electrons, it becomes electrically charged, which we define as an ion. If an atom gains one or more negative electrons, it becomes negatively charged, and we call that an anion. If it loses electrons, it becomes positively charged, and we call that a cation.
Let's actually model this electron math for a second. Look at neutral sodium. It has 11 positive protons and 11 negative electrons. If it happens to lose one negative electron, it now has 11 protons but only 10 electrons. 11 minus 10 equals a 1 plus charge, making it a cation. On the flip side, look at neutral iodine. It has 53 protons and 53 electrons. If it gains just one extra electron, it now has 54 negative charges against only 53 positive charges, giving it an overall 1 minus charge. It's now an anion.
Let's pause and check this one more time. A neutral oxygen atom has an atomic number of 8. If this atom gains 2 electrons, what is its new overall charge? And what specific type of ion is it?
Okay, let's look at the reasoning. The atomic number of 8 means it has 8 positive protons. If it was neutral, it had 8 electrons, but it just gained 2, bringing its total to 10 negative electrons. Balancing 8 positives against 10 negatives leaves us with an overall 2 minus charge. And because it's negative, it's an anion. Great job if you figured that one out. Finally, Section 5, Recap and Challenge. Time to put all of this to the test.
So, the crucial point to take away from all of this is understanding the very distinct role of each subatomic particle. Protons, they act as the atomic fingerprint. They give the atomic number and define the element itself. Neutrons add that heavy mass. Changing their number creates isotopes and alters the mass number without changing the actual element. And finally, electrons are the lightweight balancers on the outside. Gaining or losing them changes the electrical charge, creating ions.
I want to leave you with a final, provocative transfer challenge that brings all of this together. Imagine you're in the lab and you're analyzing a mysterious particle. You find it has exactly 17 protons, 20 neutrons, and 18 electrons. Based on everything we just covered today, what is its element identity, what is its mass number, and what is its overall charge? Take a look at a periodic table, apply our rules, and see if you can solve the puzzle of this particle. Thanks for joining me on this explainer, and keep exploring the amazing, invisible world of chemistry.